award session. So we have Preston Culbertson from Stanford University talking about decentralized adaptive control for collaborative manipulation. And I would like to ask all speakers to stay in the room. So we're going to hand over the award candidate certificates at the end of the session.
No, I don't. Thank you very much. Okay. Excellent. Thank you very much. So my name is Preston Culbertson. I work in the Multi-Robot Systems Lab with Max Schwager at Stanford University. And we are really interested in the problem of collaborative manipulation. So using teams of robots which can work together to move a large, heavy object. So you can think of this like when you and friends work together to move, say, a piece of heavy furniture. We also see this in nature, when groups of ants work together to move huge pieces of food back to their nests. We're really interested in trying to enable these capabilities in robotic teams. So we think this is a good idea for a few reasons. First, these teams are resilient. So for a serial manipulator, if the manipulator fails, the manipulation task will fail. Whereas with a collaborative manipulator, we can have some of the agents catastrophically fail, and still the team can complete the manipulation task. So we have resiliency to catastrophic failure. We also have really interesting things like reconfigurability, where different agents can detach themselves and reattach to other points of the payload to try to optimize some kind of performance index, and other excellent things such as parallelization. So if you have a large number of objects to be moved of various sizes, the same manipulation team can put all of the robots on one big payload to be moved, or can move a large number of small payloads in parallel. So I'm just going to start off with a simulation video from our work. This is a number of cube satellites, which are shown in blue, that are attached to a module that we want to attach to the space station, which is shown in the background. They're going to maneuver between these two asteroids in the front and connect, or manipulate this module to be close to the space station for some kind of assembly. And importantly, using our method, actually none of these robots are communicating with each other, and none of them know anything about the payload to be moved. So they're actually adapting to the unknown payload dynamics online to be able to achieve this manipulation task. So taking a step backwards, collaborative manipulation has been one of the most extensively studied problems in multi-robot systems. There have been some excellent successes over the years, including some great work by Osama Khatib and his colleagues at Stanford doing multi-arm manipulation in the 1990s, followed by a recent surge in interest that was led by multi-quadrotor lifting, work that was done by Daniel Mellinger out of the GRASP lab with Vijay Kumar, and also some excellent work doing manipulation of flexible bodies by Javier Alonso Mora and Daniela Roos at MIT. But the vast majority of work that's been done in collaborative manipulation relies on one of the following common assumptions. Most of these works rely on some kind of centralized planning or extensive communication between the agents. And again, the vast majority of work usually requires some kind of knowledge about the properties of the body to be moved. So either relative positioning of the different agents on the payload or mass and frictional properties that need to be calibrated offline. There's been a surge in work that's trying to relax these assumptions as well. So some excellent work done by Antonio Franchi and his colleagues doing some distributed estimation and control. And also some excellent work done by Michael Cora and Nathan Michael doing some recursive Bayesian estimation that appeared at ICRA last year. So in this vein, we're presenting a novel decentralized adaptive control scheme that allows a group of agents to be able to manipulate a common payload without requiring any prior knowledge about the payload to be moved, and without requiring any point-to-point communication. So no mesh network, no all-to-all broadcasting, only a common sensor measurement that they have access to. Our method has proven convergence and actually a proven bounded error, so we can actually reason in a rigorous way about the stability and convergence of our system. And this method was verified in hardware experiments using the ground robots that you can see in the bottom right. So in our problem, we consider a team of robots. It's any number of agents that you want. They're rigidly attached to a rigid body, which can move in either 2D or 3D. So all of these agents, they don't know where they're attached on the payload, so it's unknown what the moment arm is from their attachment point and the center of mass. They can't communicate with their neighbors, so like I said, there's no measurement sharing, there's no communication of like what wrenches the robots are applying to the payload. The state of the body is assumed to be a velocity, so essentially they have access to the linear and angular rates of this body in some world frame. And further, all of these robots that are rigidly attached can apply a full wrench, so they can apply a set of forces and torques at their attachment point on the body. We further assume that these robots have access to a shared measurement from some point on the body. So essentially, how this can be achieved in practice is one of the robots is going to broadcast its measurements, its linear and angular rates, to all of the robots, which they'll use as essentially a reference point on the body to know how they're doing in the manipulation task. And further, we assume that they have access to a common body fixed frame. So in essence, they know which way is up. So in our work, we first started by formulating the state space dynamics. Or excuse me, we started by formulating the rigid body dynamics of the system, which is being manipulated by any number of agents. And then we formulated this as a nonlinear state space system. So if our state is a velocity, then our derivative x dot is going to be an acceleration. And then there's going to be a few terms that are here on the right-hand side of the equation. There's going to be a linear frictional term. There's going to be a set of nonlinearities, which for 3D manipulation is going to include things like Coriolis terms, as well as nonlinear friction models that you like to include. And then finally, a sum of the wrenches that are being applied by the robots, scaled by some mass and geometrical terms. Again, we don't know the frictional properties. We don't know these matrices that are appearing in these equations. These are things that we're going to need to adapt to online. So to tackle this problem, we use something called model reference adaptive control. This is a well-known control approach that if you look at this diagram on this screen, then essentially the bottom part of this control strategy is a normal feedback controller. So essentially we have each robot running its own controller online that are parameterized by some control gains theta. And they're trying to control the system such that the state of the system, x, is able to track a desired state, xd. But what makes this different from a normal feedback controller is that we actually include adaptation laws. So we include a set of laws that tell us how to adapt the control gains online, such that we can actually keep the system stable for all time, and we can also have the system exactly track the desired trajectory. If you're familiar with machine learning techniques, this is kind of analogous to policy gradient. So essentially, we initialize each robot with some kind of policy, and then we're going to improve that policy online such that we can achieve the objective of exact tracking. So just going through our proof a little bit, we did this design of both the control laws and the adaptation laws using a Lyapunov-style approach. So we formulated a Lyapunov function over the whole system. So feeding back the control and adaptation laws, we created a Lyapunov function that's dependent on the error. So essentially the difference between our current state and the desired state, as well as the control gain error. So we could write down what the control gain should be if we knew what the body was that we're manipulating. And so our Lyapunov function depends on each agent's difference from that, from what they currently are estimating the control gains to be to what they should be. Then we take a derivative of this Lyapunov function, and 3 terms pop out. The first is a dynamics term that we can measure exactly because we have access to our desired trajectory and our current trajectory. The second is an adaptation term, so you can think of these as theta dot. They depend on the derivatives of the control gains. And then finally, a negative definite term. And all we do in our design process is we actually use our adaptation laws to cancel out the dynamics terms. So essentially using the dynamics terms that we can measure, that's how we adapt our control gains, such that we have a v dot that's negative definite. And so because of this, we're able to conclude using something called Barbalet's lemma, a well-known control result, that our error will be bounded for all time, and further that our error will converge to 0 in the limit. And so the upshot of all of this control theory is that we have proven boundedness and convergence for our method, and further, our control and adaptation laws require no exchange of information between the agents. They only require this one broadcast sensor measurement. And further, they don't require any a priori knowledge of the system. So essentially, each agent can initialize its control gains to some essentially random parameter, and then we're going to adapt these parameters online such that we can achieve asymptotic tracking by the end of the task. And I just want to bring back the assumptions that we made at the start of this talk. Of course, we're very interested in trying to relax these, and actually in this work, we've shown that if you relax these assumptions, we can still do some interesting things, although we can't perform full 6-degree of freedom control. So if we relax the big assumption, if we relax the shared measurements, so if each robot can only use its local measurements, we can actually perform rotation control. So if we imagine we stick these cube satellites to this piece of orbital debris, well, if they're using only their local measurements, because rotation's the same at all points on a rigid body, we can still control this body to tumble exactly the way we want it to. But further, if we get rid of this common body fixed frame, so each robot in its own frame has access to only its local measurements, we can still actually do rotation stabilization. So because 0 is equal in all frames, if our desired rotation vector is 0, we can still do stabilization despite not knowing what the parameters of the body are or where we're attached to it. So we verified this method experimentally in our lab using this team of ground robots that's shown in the picture to the right. These ground robots are holonomic. They were actually built in lab for collaborative manipulation. And they were all connected to a very heavy payload. This is a wood, you could think of it like a truss on a house, but essentially a wood trapezoid that weighs about 12 pounds or 5 kilograms. And actually this payload was so heavy that if any one of these robots spun its wheels as fast as possible, it would not be able to move the payload because of the static friction on the body. We fed the team measurements from one point on the body using motion capture, and all of the robots implemented the adaptive controller that we designed on board. And so now I just want to show a video of this experiment. So we're going to command these robots to track a desired trajectory. It's going to be a square wave in the x direction of the payload, which is along its longest dimensions. We initialize the control gains to be 0 initially. So at first they don't respond at all to what the reference trajectory is. And actually over the course of about a minute, they're able to adapt their control gains online such that they can achieve tracking of the desired velocity trajectory. And so actually on this slide, so we ran that experiment 50 times in our lab. And this slide shows the result, the average result over those 50 trials. And so we see exactly what we'd expect. So because the control gains are 0 initially, there's no response to this changing reference signal, which is shown in red. But over time, over the course of this minute, they're able to adapt the control gains as a group such that the payload can achieve the tracking of the desired trajectory. So just to recap our contributions, so we present a novel decentralized adaptive controller that requires no payload knowledge and no point-to-point communication to perform collaborative manipulation. Our approach has proven convergence and proven stability, and we verified our approach using hardware experiments. So for future work, we're really interested in actually formulating this in a Hamiltonian form, so a classic approach for manipulation experiments, or for manipulation tasks, which will actually allow us to reduce greatly the number of parameters, which should provide better numerical stability and better performance in practice. We're also interested in doing native position control. So our state in this work was a velocity, but we actually want it to be a position trajectory such that we can just feed the robots a desired position to track, and they can achieve that natively. Finally, we were interested in explicitly considering things like actuation limits and safety, and also to relax the broadcast that we used in this work. So essentially to have robots use only their local measurements to be able to achieve this global tracking that we have in this work. So this is our contact information. Please reach out if you have any questions about this work, and I'm happy to answer any questions. Thank you so much for your time.
Thank you so much. I'm sure there is a question or two in the audience. There's Richard.
Thanks, it's a really elegant piece of work. If you violate the rigid body assumption, so the object is slightly flexible, does the performance degrade gracefully?
So actually, a strength of this work using the adaptive controller is that if the body parameters vary slowly, then actually, because we're estimating these body parameters using the adaptive controllers, then they can respond and actually adapt their control gains to match that flexibility. Of course, if the body is like a net or a sheet, then those are going to vary very quickly, and so then the assumptions are kind of invalidated, and so this Lyapunov proof that we present is totally out the window. So it kind of depends on the timescales that we're talking about and how quickly we're adapting our control gains online.
We have one more question. Then I have one. Oh, there is one. Can we get the microphone over here, please?
Thanks for a great talk. I learned a lot. So I have a question. So in the experiment, you showed the set of robots moving linearly, if I got it right, back and forth. If now the commanded velocity is orthogonal to that direction, do they have to go again through a phase of system ID of the controller?
Absolutely, yeah. That's the exactly correct intuition. So the adaptive controllers are really only going to adapt the control gains as much as they need to be able to track the reference signal. So if you provide a very unexciting reference signal, like we did in that experiment, so we're only exciting the payload along one direction, the control gains are only to be evolved such that they can track the payload, the reference trajectory in that direction. So if we send a reference signal suddenly in the orthogonal direction, then of course the tracking is probably going to suffer. There's going to be a transient phase where the controllers are readapting, but then given our proof, actually they still will be able to converge and now track the more exciting signal, which excites the payload in both directions.
All right, thank you so much once again. Before closing this session formally, I would love to ask all speakers and authors, actually, to come back on stage. So we're going to hand over the certificates for the award finalists. I would also like to mention, and Richard is looking at me already, that this paper presented, the third paper here in this session, is also nominated for the award for multi-robot systems. But if I'm not mistaken, you're not going to be presenting twice. So you nominate, it's one presentation, but you're nominated for 2 awards.
Exactly.
So just to make sure that I get this right. So we have, I'm not sure whether someone is taking pictures. We're going to hand over this award to you.
Perfect. Thank you very much.
Thank you.